Hi, welcome to the 10th live session of Points of Topology 1 course. This is Shovik and I'm working on discussing my elementaries. This is the 10th live session of Points of Topology and video course. So in last day we have so in the last day we have gone through the notions of separability and countability. And today we thought, in last week we thought that we shall discuss the assignments. Today we shall discuss the assignment, but before doing that, first we shall um, understand important concept of point topology, which is actually very useful algebra topology, and which is actually the gateway of algebra topology, namely the quotient topology. Okay, the quotient topology comes inside the syllabus of the quantity topology. Okay, so this quotient topology, okay, it's not. Look, quotient topology is not advanced. It's not advanced at all. But the point is, you need to understand the importance of quotient topology, and you need to understand some intuition in order to do work with the quotient topology and all. Okay. So first, let's start with the quotient topology, and if time permits, then we shall go with other things. Okay. So today we shall start with, wait a minute, sorry. Yeah, wait. What happened with pen actually? Sorry. Oh, sorry. Sorry for the whole mess. Okay. So today we shall start with the quotient topology. Okay. So let's get into definitions. Okay. So sorry. Okay. So before, okay. So before going to definition, first we shall try to understand. Oh, wait a minute. Okay, first we shall try to understand the important question to what is important and what is the intuition between all these things. Okay, so intuition is important. Okay, so hence, so namely, suppose, uh, suppose, so suppose we have a rectangle. Okay, now if we join the now if we join the b side, then what we will get? We will get something like a cylinder, right? Where this side becomes little b and all these sides become a and a, right? Now, if we again join the a sides, what we will get? We will get something like a torus. Like for example, so this looks like a torus. This is this, and this is what we will get, right? This looks like a total. So basically, after doing the age identification, I mean, after doing the ages, so this is what we doing is something known as the gluing. Sorry, gluing. Okay. So we are gluing the vertical edges, then we are gluing the horizontal edges, and what we are getting is getting a torus, right? Now the point is the following. So what we'll get? So we started with a topological space, and by gluing some portions of this or gluing some subspaces of this to a single thing, we are getting some new space. Okay. Now, the point is that the study of this thing in topology is no comes under the study of the quotient topology. Okay. For example, so instead of gluing the rectangle above, if we take the rectangle this and this and gluing this vertical like in the opposite direction, what we will get? We will get something like this, right? It is like it is known as a Mobius band. Okay, and it is a one very interesting object in topology actually. Okay. So basically, this method of gluing things are known as a quotient topology study. And for example, suppose we have a disk. Sorry. Yeah. So suppose we have a disk, okay, and we are joining this boundary to a single point. So what we will get? We will get this thing, right? Correct. So also basically, this is the boundary. Sorry, this is the boundary, and we are gluing this into a single point. Okay. So yeah, so this is it. So yeah, so these are the, so I mean, you can take this as a motivation. Okay. Now of course, so basically disk. So what is this thing? This thing is typically disk. Sorry, identified boundary to a single point. Okay. So what is, so these things come under a question topology, and we shall prove this mathematically. I mean, these examples are visually okay right now, but we need to prove this mathematically, right? So gradually we'll see these things. Okay. So first, let's start with the definition. So first, let's start with what is the definition of quotient map. Okay. Okay. I shall be back after some minutes. Okay. দেখি চেয়ারটা। Oh shit. 3 2 2 0 9 2917 এমন ভাবে প্রিন্ট করা আছে চোখেই পড়ছে না ঠিক করে এটা খুব জটিল কাজের চোখে পড়া ফোনে আলো টর্চ দিয়ে দেখি খুব জটিল আছে না এই যে 29 17 24 ওটা 29 17 24 ঠিক আছে হ্যাঁ এবার ঠিক ঠিক আছে Yes. masih ah okay. So let's get to the definition of the quotient. Okay. So what does it mean by a quotient? Sorry, just wait a minute, please. So the definition is follows: let x and y be topological. Let p x to y be a surjective. Okay. Then p is said to be a quotient map if u subset of y open if and only if p subset of y open if and only p inverse of u open inverse or equivalently if subset of y closed if and only if p inverse f was x. Okay. So this is a definition of question. So of course, so question map is a obvious continuous map because of this definition, and question map is by definition subjective. Okay. Well, so that is the definition, but in reality, there are some tricks to prove that given map is question map or not. Okay, so proving a map is a question map is not a matter of joke always, because some maps are very tricky that you can't directly go with the definition. You need to use some technique or some trick in order to prove that some given map is a question map. Okay, okay. So, okay. So there are some good situation when a given map is a question map. Okay. So fact one. Sorry, wait a minute. Shit. So subjective. So subjective open map question mark and subjective plus closed family question mark. So by the open map is send open to the open, the closed map is send closed to the closed. Okay. So this is definition. Also, there are some situation where given now, well, so okay, so it is sometimes easy to determine whether given map is open map or not, but it is not always easy to determine whether given map is closed or not. Okay, so for that there is a criteria. So there's a fact. So let fx to y be surjective. Now such that x compact and y house dot. Then f is closed. Wait a minute, please. This closed map and hence. So how? Okay, so, oh well, I shall be back in 2 minutes. ইয়ে কি বলে জানো, লবণ কতটা দিচ্ছ দেখি? আহ কতটা দিয়েছো? হাত দিয়ে দেখো, কতটা দিয়ে? আহ দেখি দিকে দেখাও, লবণ অত লবণ এইটুকু না, হাতের আঙুল যত ততটুকুই দিবা। তুমি যতটা দিয়েছো ওটাও বেশি হয়ে গেছে। হ্যাঁ, অতটুকুই দিবা লবণ। আমি অত লবণ খাই, আমি লবণ কখনো এত খাই না অ্যাকচুয়ালি। এগুলো আর সিমের বীজগুলো ছাড়িয়ে দিয়েছো? বীজগুলো বলছি না। সিমের বীজগুলো সিমের বীজ, ঢেঁড়স কি? সিমের বীজ, সিমের বীজগুলো ছাড়িয়েছো? ছাড়িয়েছো তো? ছাড়িয়ে দিয়ে সব ছাড়িয়ে দিয়েছো তো ওগুলো? ঠিক আছে, তাহলে ঠিক আছে। আর তেল একদম সামান্য দিবা। সকালে যতটুকু তেল দিয়েছিলাম তার থেকেও কম দিবা। হ্যাঁ, কম দিবা তেল। হ্যাঁ, বেশ। হ্যাঁ, হুম। So how to prove this? Since so the proof is the following. So since x compact, so basically we need to prove that it is a closed map. So what we will take is the start of the closed map not only. So let f be a closed subset capital S. Okay. Now since x compact, so f is compact. Now since, I mean, of course, if it's surjective plus continuous, continuous is obviously there. So being f continuous, so f of f is also compact subset of y, and y house dot. So if f is closed, so we have started with a closed set when we come up with that f is a closed set, hence it is a closed map. So f is a closed map, hence quotient map. Okay. Hmm. So we call it a quotient. Okay. So this is so basically so for now onwards, I mean in most of the situation, if it's some situation, if you so see that the domain is compact, code of a house drop, then it will be a quotient. Okay, that's all. So there's one technique to identify the quotient or not. Okay, but so we have seen the open map or closed map, subjective, the quotient map, or of course, I mean one may guess that reverse is not true. But okay, so we'll see the reverse not true thing soon. Okay, so okay, yeah, okay. So okay. So let's get to reverse not true. So this is an example of quotient map, but not open map. Okay, so define P for close 0 1 union close to 3 to R. Okay. Now first you try to think that why this is a quotient map. Okay, as the back of 2 minutes. আছে এই চ্যাটটা মুছতে হবে ওই চ্যাটটা আমি এখন চেঞ্জ করে নেবো এই চ্যাটটা একটু পিছন পোর্শনটা বসে জায়গাটা মুছে না look. Ah, okay. So P equal 0 map like this. Okay. So first question is why. I mean claim is that P is a quotient map, but not open map. Now question is why. So firstly, what is the question? So look, with the domain of P, I mean, so first, just try to just one important observation of what this map is doing. So this is 0, 1 and this is 2, 3. So basically what this map is doing, this map sends 0, 1 to 0, 1 and sends 2, 3 to 1, 2. Okay. So basically this map is identifying this point 1 and this point 2 by this map. Okay. Super understanding. Okay, so anyway, what is the piece of question now? The reason is that domain is compact and codomain house drop, right? Domain compact, codomain house drop, and P is surjective. So it is portion. Okay. Certainly, a minute. Hmm. Hmm. Okay, so it's a question, but it is not open. Why? Because what it so first uh, observe that close 0, 1, since close 0, 1 is open in close 0, 1 union 2, 3. But its image is what? Close 0, 1, its image is close 0, 1. This is not open in close 0, 2. So P is not open. Okay, so that's why. So I mean, so this is one example of a question map which is not an open map. Okay. So similarly, we'll now see an example of a question map which is not a closed map. Okay. So the this example is like, wait a minute. Example of a quotient map, but not a closed map. Closed map, but not a quotient map. How? So so consider the first coordinate position pi r cross r2. First coordinate projection, that is first coordinate projection. So firstly, to claim pi 1 is a quotient, but not closed. The answer is why. So we know that pi 1 is open, right? It is already known. And of course it is subjective. And of course subjective. So pi 1 is the quotient. But it is not closed. Why? Because so if we consider this set pi 1 of all those point x y, so the x y is equal to 1, that is this part, the hyperbola. Then pi 1 of this thing is what? Pi 1 of this thing is r minus 0, right? This is not closed in r, okay? So pi 1 is not, but this thing is closed not. So pi 1 is not closed. So pi 1 is quotient but not closed. Okay. So this is okay. Yeah. So okay. So okay. So I said a backup to sentence. Okay. So okay. So till now we have seen different examples where given map is the question map, not open map, etc. and all. Okay. So now going beyond this, so there are some new things which are known as the quotient topology or a quotient space and all. Okay. So now let's get into this. Okay. So first the definition of a quotient topology. So let X be a space and capital A, B is set. And if Px to A is surjective, then there exists unique topology on A with respect to which P is a quotient. And so, of course, it is what? It is all those subset of U open such that P inverse U is open in X, right? And it is known as quotient topology induced by little p. Okay. Right. Okay. So, hmm. So for example, P from R to capital A, A, B, C with a map defined by x equals to is greater than 0, B if it's 0 and C if x equals to 0. So of course, B is such. Okay. And the quotient topology on capital F induced by P are what? Are all inverse images of open subset of capital. So these are what? So these are B, A, B, A, B, C, 5. This is the inverse image of 0 infinity. This is the inverse image of minus 0. This is the inverse image of minus 0. These things are anyway open. Okay, so that's why. Okay. So this is how we can define the quotient topology with respect to which the given map is the quotient map. Okay. Now there is some another concept known as the quotient space. What is this? So let for the quotient space, let X be a space and let tilde be an function of X. So then let X term be the so I mean any equalization give the partition, so be the partition on X associated with the star. And let P be the natural surgery book, namely X goes to class of. Then quotient topology on X star induced by P is called quotient space of X. Okay, do the definition. So what is it? So basically, capital X, we have a space, and there is a relation tilde. Say we have considered X upper star, which is a partition of capital X into disjoint equivalence classes, and there is an obvious surjective map. This surjective map is each element to its equivalence class, and then the quotient topology on X upper star generate induced by the map little P is called the quotient space. Well, so this is the definition of quotient space. Okay. Now the problem is that okay, so this is a mathematical definition, but in general we need to show that all these things are homeomorphic to some well-known space. For example, which uh, yeah. So so the first example of rectangle where we have glued for the vertical line and glue the horizontal of what? So gluing the vertical lines so equal relation on the cap in the rectangle, and under the sequence relation, uh, 0t are identified with 1t, and here also this part and this part identified. So this two and this top one is what? S0 identified S1. And so after doing this rigor relation, this is the torus we think. So basically what we want to prove mathematically is that X upper disturbance quotient space is homeomorphic to this thing. This is actually what we need to do. Okay. Because in reality there are many examples where it is not possible to visualize. Okay, here we can actually visualize, but well, the proof is not easy yet. The proof is difficult. It is not something direct. Okay. Hmm. So, in the second example, also where we have identified the disk of boundary, I mean the boundary of a disk to a single point with a sphere. Okay, so they are also someone to show that the quotient space is homeomorphic to the sphere. Okay, well, so before getting into the proof of this thing, let me give some intuition from Wikipedia that the disk with boundary identified will be the sphere. Okay, so let me open the Wikipedia. Disk identified the boundary to single point. So there is a let the quotient part. So this is the so this is the disk ID with the boundary, and you can check that. Wait a minute. For boundary identified, and gradually it is going to a sphere. Okay. So intuitively, what we can do is that you can take you can consider this to be a closed upper hemisphere, and you're identifying the boundary with the closed upper hemisphere. So of course, then it will be a full sphere, right? So that's why. So that's the intuition, okay. But proving mathematically is not easy task. Okay. So let's get back into the original discussion. Okay. So first, we try to show that the rectangle with with the horizontal identification and the vertical identification with the torus. So let's first give the definition of torus. Okay, so and then we shall prove that a disk with boundary identified for single point is homeomorphic disk. Okay. So for that we need to prove the first this fact. Let X be a compact Hausdorff space and capital A be closed subspace. In the quotient space, X by A homeomorphic to the one point compactification of X minus. Wait a minute, please. So basically, so what, I mean, how to prove this? So basically, we need to prove that quotient space is the one-way multiplication of x minus a. So first, we need to somehow show that x minus capital A lies inside x by x quotient A, and there is only one single point difference for to be the whole solution. So what you can do, x minus a can lie inside capital X, and x2 x by the quotient little q. So this, so basically, this is an embedding x minus a is locally from that house drop, and q of x minus a, I mean capital, I mean this is equal to x by a minus a single point, right? So this thing x minus a is one multiplication with x by a. Okay, this is one thing. Okay, so yeah, so that's all. Now using this, we shall try to show that dn quotient boundary is isomorphic. Okay. So of course dn is compact and boundary is, so basically dn by sn minus 1 is same. Now, of course, dn by Sn minus 1, it is homeomorphic to 1 by multiplication this thing, okay? dn minus Fn minus 1 is equal to open ball 1 by multiplication. You know, open ball is homeomorphic to the Rn 1 by multiplication. Rn is 1 by multiplication. So this tells that dn by Sn minus 1 is same as Sn, okay? So this is the proof. So yeah, as you can see that the proof is slightly, the proof is really tricky and okay. So in the question topology, in many standards, you may face this type of similar situation where you can directly see what is the answer, but you can prove, but that's okay. I mean, there are lots of things, there are lots of tools you are using to prove this. Okay, so nobody knows that which tool will be used in order to prove something new. So that is drawback of question topology. But that's why it is important to first make a possible guess at least. Okay. Now, now we shall prove that. Now we shall prove that the rectangle with 105 is the torus. So first we shall define a torus. So torus is same as S1 plus S1. Okay. For the time being, keep this thing in granted. Though to S1 plus S1 lies in R4 and torus lies in R3, but torus is an immersion of S1 plus S1 inside R3. Okay. Yes, sir. So, so now, wait a minute. Oh, wait a minute. Okay, so, wait a minute. Ah, Ah, so basically, uh, hmm. So instead of torus, we shall go this one. Okay. So rectangle is close 0 1 cross cross 0 1 2. We have to some map should this. Okay. The map will follows S comma T go to e to the power 2 pi I S goes to e to 2. Right. So under this map, so first P is a surjective, which is obvious, plus continuous map, which is also this is okay. Now domain compact plus codomain house club. These implies P quotient. So so is a question. Okay, now observe that 2.0t and this 1t, this thing under P, it goes to same place, and also P of S0 is equal to P of S1. Okay, so by the property of the quotient close one is squared, this relation, this x star, that is this star is isomorphic homeomorphic with S1 cross S1. Okay, so this is the proof. Okay, well, so well, in order to prove this thing rigorously, so there is a theorem for that. So okay, so what I've seen is that if we have the rectangle, if we are identifying those being the vertical edges and the horizontal edges, then the new quotient space is the homeomorphic case on process. So now we want to prove this thing. So how to prove this? So well, wait a minute. Hmm. Okay, so the corresponding theories are as follows. So now there, so these are the some. Okay, I see the back. Okay, so so the statement of the theorem is as follows. Let P X to Y be a quotient map and let tilde be an equivalence relation on capital X such that x related to y if and only if x equal to y. Then the quotient space x star is homeomorphic with capital. So this is the actual statement of the theorem. But now, mm, okay. So what is the thing? So we have some map x to y quotient map. So that, and suppose there is an equivalent. Equivalent is what? So in torus case, what are the equivalent relations? 0t, 1t are identified for each t. X0, x identified by each one. Or in case of this, that each boundary point are equivalent. Okay, in this way. So so two points are equal, or that equal. If such a thing happen, then this x star is homeomorphic to capital Y. Okay. How? So so this is the statement. Okay. So using this, let's now prove some other things. Some let's do some exercise or some other. So now in the following exercise, we shall see a way by which a given map is a quotient map, because directly something proving is a quotient is a difficult task. Okay. So So, mm, oh, so let Px2 by be continuous. Catch that there exists a continuous of f in the reverse direction y to x such that P compose f is equal to identity of y. Then P is a quotient map. Okay. So how to do this? So okay. So we need to speak the question. So first, P composable identity. These similar what? These similar P surjective. Okay. So that this thing fine. And of course, P continuous. It is given. Now we need to show that U subset of Y open P. Now only to show if P inverse U open. This implies U open, right? So what we are doing? We are doing F inverse of P inverse U is equal to U. Okay. So now, so this thing is U. Now, if P inverse U is open, then by continuity of F inverse of P inverse of U open, and this thing is equal to whole of U, this is capital U open, right? So this is what P inverse U open implies U open. So this implies P is quotient map, right? Okay. So this is the thing. So this is one way says the so what is P comma identity means if there is a map X to Y. So if it admits a section, then it will be a quotient map. Okay. Now, so this is one way understand by map. Okay. Now, so if a subset of X in a retraction of X onto capital A is a continuous map letter R capital X to M lay for each A belongs to A. Show that retraction is a quotient map. Okay. So so using the above how to show retraction question, look. So since retraction is what? Capital A to X to A R and R composite identity of M. So then due to by the previous fact, little r is a quotient. Okay. So this is the argument. Okay. Now let's try to solve something based on the intuition. So, so we have x equal to r square. Okay? So here we're defining an equivalence relation, namely y0 related to x1 y1 only x to the square plus y. Okay. Now the question is this: the question is x star is familiar to x. So how to solve Mr. Problem? So basically we have real line, okay, and we have some concentric circles. Okay. Now in the question space, this point, so this point are equivalent to all the point. The first circle, this point equal to all the point. This third one equal to first. So if we consider this right hand side x-axis of R2, then possibly capital X star should be homeomorphic to 0 close 0 comma open. But now we need to somehow prove that this thing capital X star is homeomorphic to closed infinity. So how to prove? So we are going to define a map this to this, and what we are doing, x to y goes to x square plus y square, and in the reverse direction we're defining map to capital x goes to root over x. Okay, yes, obviously P composite is the identity, so P is the quotient map, and 2 points, and P x comma y is equal to P x prime for y prime if and only if x y related to x prime for y prime. Okay. So by that theorem, the quotient space x star is homeomorphic, close zero, open infinity. Now, So okay. So I mean, so this is the so I mean, so this is the way we can first try to make a possible guess to understand how a question is placed might look like, and then using those theorem we need to prove those things. Okay. Well, so let's let the time here. Okay. So let's end here. So this is the that's all for the question space. So today, so we shall on the on the next day, on the next live session, we shall actually start to solving the assignments. Okay. If you have any doubt, you can email me. I will definitely reply. Okay. Thank you. I will leave the session.